set we covered GATE 2016 for the electrical branch SET1. So in this series we are going to start with SET2 of 2016 paper, and here is question 1. The output expression for the kernel map shown below is A, B, C, D. We have been given 4 different options. So kernel map is also known as K-map. This comes under switching theory and logic design. I'm sure you've already guessed. Now the map given to us shows for A, B and C we have got 8 cells, and you know how that comes. A, B and C, these are our inputs. Now they have 8 different combinations. I'll just write that down here for you. Considering the binary bits in this case, so we have A, B and C, and you will see that there are altogether 8 combinations. Now we require the output F of the kernel map given to us. So this, we will have to consider only the part where the ones are given in this map. So let me draw that out for you as well. In general, the K-map with 8 cells, are named M0, M1, okay, this is for A, B and C, M3, M2, M4, M5, M7 and M6. Okay, so the value for each of these cells are 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. Okay, let me quickly just give you a rundown of how this K-map actually has these values. So you see A has got two values of 0 and 1, the possibilities here, and BC, the values are 0, 0, 0, 1, 1, 0 and 1, 1. But when they are arranged, you will notice that 1, 1 is placed in between here rather than at the end. Now the reason is because they are arranged so that just there's one change from 0 to 1. There cannot be both changes. Now for example, let's take a look at this. Here the value of BC is 0, 0. In this case the value is 0, 1. So from 0, 0 to 0, 1 there is just a change of C. C changes from 0 to 1 while B remains 0 to 0. Now B cannot change as well. There should be just one change. Similarly here now, BC is 0, 1, BC is 1, 1. Now what is changing here? You will notice that only the value for B is changing from 0 to 1, while C remains C remains the same. Now if we were to place 1, 0 here, you would notice that both B and C are changing. Both are changing. Now we don't want that. We don't want, there shouldn't be change in both B and C. There should be just one changing. That's the reason they are arranged this way. M0, M1, M2 here, and then M3. Similarly in this case as well. So M0 to M7 are arranged. That's the output here. The first would be M0, M1, M2, M3, and so on and so forth. So that's just the general outlook of how kernel map for 8 combinations is written. Here, each of these values correspond to these values over here. Now, in order to write the output expression, we need to look at just the ones in this map. So we have ones here and ones here. So the next step is to group them or pair them up in 2s, 4s and 8s, because the total number is 8 and we have to pair them up in even numbers. So the pairing we have in 8s, 8 ones, okay, in 4s and in 2s. Now we see that there are just 6 ones, so 8 is ruled out. We cannot group them in 8s. In 4s next, we see that there is one way of grouping the ones here. So we have just one group of 4 ones. So that's one group. We have one here. Now next we see if we can group them in 2s. We can group them in pairs. So we have one group here and then we have another group here. So altogether we have 3 groups. Now the output expression is based on these 3 groups. I'll note that down here. So the output is F. Alright, so the output is F. Now let's take the group, the largest group in 4s that we have grouped here. So we see that A is 1 and B and C is changing all over. So because there is a change in B and C, we ignore that. We leave that as it is. We concentrate on the term that is not changing, and that's A. A is not changing. So because the A value is 1 here, we note that down as A. That's our first term, A. If it was 0, then that would be written as A bar. You should know that. Okay? So next, we have, let's look at this group here, the 2 ones here. Now we see that BC is 0, 0, 0, 0. There is no change in anything else. Therefore, we use that. Now here A, there is 0 and 1. So there is a change. So we remove that. We ignore that. We don't consider that. We consider the BC, which is not changing. And since the value is 0, 0, how do we write that? We write that as B bar, C bar. Next, we have this group here. Now this group here, again, the values of A is 0 to 1, which is changing. Ignore that. Take the value BC here. Now BC for both these ones remains the same. So the value of B is 1, the value of C is 0. So that's B, C bar. B, C bar. Okay, so now we have to try and simplify this in order to get one of these options that's given to us. So that's F is equal to, let's take C bar common here, A or C bar, we have B bar or B. Okay, so now according to the rules, we have a rule here, Boolean rules, which says that A or A bar is equal to 1. Now using this rule here, this becomes 1. And that leaves us with F is equal to A or C bar. So this is our final expression. That matches option B. So option B is the final answer. I hope this has helped. Okay, so here's the next question, number 2. This is for 2016 electrical paper set 2. So the circuit shown below is an example of, we have our 4 options, low pass filter, band pass filter, high pass filter and notch filter. Okay, so let's look at the circuit given to us. Now this is an operational amplifier circuit, or also known in short as an op-amp. So we have an op-amp here, and we notice that there is a feedback path, and the feedback path has a capacitor in it. So that should give you a clue, because an ideal integrator has a feedback path with a capacitor in it. So I'll write that down. Ideal integrator is an inverting amplifier that has a capacitor in its feedback path. Alright, so it is these clues that enable you to find out which type of filter it would be. So an ideal integrator is the one that has a capacitor in its feedback path. So the next step is to see what the ratio of the output to the input is. Now if the output to the input indicates that it is indeed an integrator, then that will tell you that it would be a low pass filter. So let's just check that out now. Let's look at the ratio of V out to V in. Now V out to V in, let's note that down as Z2 by Z1. Now because there is a feedback path, I'm including that as a negative. So that's minus Z2 by Z1. So we're taking it in terms of impedance here, the ratio. So minus Z2, in terms of what we have here, we have a capacitor. So we write that as 1 divided by SC by Z1 is R1. So let's just note that as R. Now if we simplify this, we can write that as minus 1 by SCR. Now to put this in better perspective, we can say that the output is minus 1 by SCR times V in. Okay, so if we were to convert the S in terms of time domain, then we can simply write this as V output is equal to minus 1 by RC V in. Now this is in our time domain. Now if we integrate both sides, we get V out, this is dot. Now if we have to convert it into S domain, this is V out dot, so that's differentiation. So this is a derivative. This equation is a derivative, please keep in mind. So this is in time domain. So this is the derivative, and in order to find out what V out is, we integrate on both sides. So when we integrate on both sides, we get V out is equal to minus 1 by RC integral V in. So this is the general notation, a very quick view of how we see the output in terms of input, which is an integration of it. So because of this equation, we see that the circuit given is indeed an ideal integrator. Now if it is an ideal integrator and has a capacitor in its feedback path, it represents a low pass filter. So that is our final answer. I hope this has helped. Here's the next question, number 3. The following figure shows the connection of an ideal transformer with primary to secondary turns ratio of 1:100. The applied primary voltage is 100 volts RMS, 50 Hz AC. The RMS value of the current I in amperes is dash. Okay, so this is not a multiple choice question, so we will have to be careful in working it out. So we have been given an ideal transformer with all the ratings as you see in the figure here. So the first thing we do is to try writing or transferring the secondary parameters to the primary side. Since we are asked to find out the value of the current in the primary side, so let's shift everything to the secondary to the primary side and then write an equivalent circuit. While doing so, we will be able to find the current, the RMS value of the current. So first, let's transfer the secondary parameters to the primary side. Now in order to do this, we have to find out two specific values. We need the value of R1 and XC1 or XC dash. So these are the two values that we need in order to draw the equivalent circuit talking about secondary parameters, transferring them to the primary side. So these are the two values that we require. Now here is the formula. I'll just write that down here. R1 can be found by multiplying the given value R with the ratio of V1 by V2 square. So this is the general formula. Now if we were to substitute the values, we have R given to us as 80K, 80 into 10 power 3, and V1 is given to us as 100 volts RMS. So that's 100 divided by V2. So V2 is the voltage, the primary voltage times the number of turns that is given to us, that's 100. So the ratio is given to us as 1:100. Now this ratio should tell us what V2 is. If V1 is 100, then V2 will be 100 times 100. I'll put that down here. V1 is 100, then V2 is 100 into 100. So that's V1 into the number of turns according to the ratio given. So here we have 100 into 100 square. So let's see now, 100, so that's 1 by 100, and that would give us 8 ohms. So the value of R1 here is 8 ohms. So the next thing is to find out what the reactance is. So XC dash. So let's find out what this is. We use the same formula. We have XC this time multiplied by the ratio V1 by V2 square. Now XC given to us is 40. So that's 40 into 10 power 3 into the same ratio, 100 divided by 100 into 100 square. So we get here 4 ohms. So we have the values of R1 and XC dash. Now let's draw the equivalent circuit. I'll just get another sheet of paper. Right. Okay. Now here are our values. R dash or R1 is given to us, we have found it to be 8 ohms, and XC dash is 4 ohms. Okay, so now we need the equivalent circuit. So the equivalent circuit can be drawn, forgive my drawing, it's a little rough. Right. That's about it. Okay, so we have the value, the RMS value given to us as 100 volts. Here we have J10 as given in the diagram here, 10. 8 ohms of what we have found, R1. This is XC dash. Now, this is minus J4. Please keep that in mind, alright? It is quite important. So here for the capacitive reactance, we have it as minus J4. Now this is XL, the inductive reactance. So that would be positive. Well, whereas for capacitive reactance, it would be negative. Now, let's calculate. We need the current. Now, in general, we know what the formula for current is, right? So, current I, V by R. Our very general formula. So, let's utilize that in order to find our value. I is equal to, we have 100 divided by the sum of all of this. So, that's resistive 8 plus J10 minus 4. Now, in order to find out what the magnitude is, we find the resultant, and the resultant would be 100 divided by root of 8 square plus, here we have 10 minus 4 square, and that gives us 100 divided by root of 8 square plus 6 square. That's 100 by 10, and that gives us 10. So 10 amps is the RMS value of the current. So that's our final answer here. I hope this has helped. Here's the next question. Number 4. Consider a casual LTI, linear time invariant system, characterized by differential equation dy by dt plus 1 by 6 y of t is equal to 3x of t. The response of the system to the input x of t is equal to 3 into e power minus t by 3 u of t, where u of t denotes the unit step function is, we have our 4 options given to us. Okay, so here the system has been characterized by the differential equation. So let's just write down what the given equation is. That's dy by dt plus 1 by 6 y of t is equal to 3x of t. And the input is given to us as x of t is equal to 3 e power minus t by 3 u of t. Okay, so one way of solving this is to first use Laplace transforms, convert it into the S domain, and then try and figure out by using inverse Laplace again to get the final equation. So let's do that. I'll just take another sheet of paper and we'll begin. Right. Alright, so we have our equation. Let's start with the equation given to us. The characteristic equation is dy of t by dt plus 1 by 6 y of t is equal to 3x of t. So let's take Laplace on both sides. Taking Laplace transforms on both sides. So we write that as, that's dy by dt plus 1 by 6 y is equal to L 3x of t. Okay, so when we apply the Laplace transforms here, we can write this as s plus 1 by 6 times y of s is equal to 3x of s. Alright, so the Laplace transform of dy by dt plus 1 by 6y is s plus 1 by 6 of y of s is equal to 3x of s. Now let's take the ratio of y of s to x of s. Y of s by x of s can be written as 3 divided by s plus 1 by 6. Okay, so we have the ratio here. Now the next thing is we already have what x of t is. Now the x of t is given to us, the input is given to us. So the input here, x of t is given as 3 e power minus t by 3 u of t. Now u of t is a step function, so we can consider it to be as 1. The value of this is 1. So let's just concentrate on 3 e power minus t by 3. Now 3 e power minus t by 3, applying Laplace to this, I'll put that here. So Laplace of the input x of t, okay, is Laplace of 3 e power minus t by 3. And the Laplace of that would be 3 divided by, we have e power minus t by 3 here, s plus 1 by 3. Okay, so the Laplace of e power minus t by 3 is s plus 1 by 3 in the denominator, 1 divided by s plus 1 by 3. Now I suggest that you keep the list of formulas by you while you are solving this. That will help you out. Okay, so this is our input. Now let's substitute this over here for x of s. Now this is x of s. Okay, so if we were to substitute that here, y of s divided by this. So that's 3 divided by s plus 1 by 3 is equal to 3 divided by s plus 1 by 6. Okay, so now we have an expression where we need to find out what y of s is. So let's take this term to the other side. I'll just take another sheet of paper and we'll continue. Okay. Alright, so we have y of s divided by 3 by s plus 1 by 3 is equal to 3 divided by s plus 1 by 6. Alright, so we are now going to take this term to the other side and we get that, and we get the expression for y of s 3 by s plus 1 by 6 into 3 by s plus 1 by 3. Okay, so this is what we have now. In order to solve this further, it is important for us to find the partial fractions. So that's going to be our next step. Now, I'm sure you have already, you're quite familiar with how to find partial fractions for equations, but nonetheless, we'll just solve it here real quick. Okay, so now in order to take the partial fractions, we have to consider each term, and we write this as y of s is equal to a divided by s plus 1 by 6 plus b divided by s plus 1 by 3. Okay, so we are taking partial fractions here and we have to find out the values of a and b. Now these two constants we will have to solve. So let's call this 1 and let's call this 2. So we have to equate both of this in order to find out what a and b are. Okay, so let's just write down the values. Alright, now if we solve these two, we can write this as y of s is equal to a s plus 1 by 3 plus b s plus 1 by 6 is equal to, now y of s, right, we are going to equate both the equation 1 and 2. So once we cross multiply, we have our numerator and then the denominator would obviously cancel out if we are equating 1 and 2. So we are left with 3 times 3, which is 9. I hope you're following what I'm doing here. We are equating 1 and 2. So if we cross multiply, in other words, we are just equating the numerators of 1 and 2. Okay? So we have a into s plus 1 by 3 plus b into s plus 1 by 6 is equal to 9. Now we open up the brackets and let's see what we get. As plus a by 3 plus bs plus b by 6 is equal to 9. Now in order to solve this, we have to equate the coefficients of s from both sides to get one equation and the constants to get the second equation. So that's how we get two equations here. So let's first see the coefficients of s. Now the coefficients of s, we have one term here, no term on this side. So that gives us a plus b is equal to 0. That's our first equation. Now the second, we equate the constants alone. So the constants are a by 3 plus b by 6 is equal to 9. So these are the two equations we solve for a and b. Now when we do, we get a is equal to 54 and b is equal to minus 54. Now since this is basic, I'm leaving that to you. Alright, so we have two equations, linear equations in two variables. Solve for a and b. You will find that a is equal to 54, b is equal to minus 54. So we substitute the values of a and b in equation 2. Okay, so a is 54, b is minus 54. We substitute it in equation 2 to get y of s is equal to 54 divided by s plus 1 by 6 minus 54 divided by s plus 1 by 3. So this is the expression for y of s. Now we take inverse Laplace. Applying inverse Laplace on both sides, we get y of t is equal to, now 54 divided by s plus 1 by 6 is 54 e power minus t by 6 minus, now the Laplace inverse of this term is 54 e power minus t by 3. Now since the question mentions that u of t is a unit step, that's what the question says. Let me just go back here, see. Now the u of t denotes the unit step function, so we need to multiply this expression with u of t. So the final expression would be y of t is equal to 54 e power minus t by 6 u of t minus 54 e power minus t by 3 u of t. So this is our final equation, and that matches option, let's see, that matches option D. So this is our final answer. I hope this has helped. Here's the next question, number 5. Suppose the maximum frequency in a band limited signal x of t is 5 kHz. Then the maximum frequency in x of t cos of 2000 pi t in kilohertz is dash. Okay, so this is not a multiple choice question, so we will have to work it out. Now we have been given that the band limited signal, or the maximum frequency of x of t is 5 kilohertz. And the signal that has been asked of us is x of t cos of 2000 pi t. Now if you will notice here, we can split this and write it as x of t cos of 2 pi into 1000 t, because usually we write it as 2 pi omega t. So that's why in splitting it, we'll be able to write it as 2 pi times 1000 t. So I'll just write that here. The form of which you have to note is usually in terms of 2 pi omega t. For any trigonometric function, this is the usual notation. So in using this notation, if we split it, we get it in terms of 2 pi into 1000. So 2 pi into 1000 is 2000 pi t. So if x of t, the maximum frequency is 5 kilohertz, so for this we will have to add the 1000 or the 1k. Let me write that here. So the highest frequency component would be the given maximum range of 5000 plus the omega that we have found over here, plus omega, which is 5000 plus 1000, and that's 6000. 6 kilohertz. So 6 kilohertz is the final answer. I hope this has helped. Here's the next question, number 6. Consider the function f of z is equal to z plus z conjugate, where z is a complex variable and z star or z conjugate denotes its complex conjugate. Which one of the following is true? F of z is both continuous and analytic. F of z is continuous but not analytic. F of z is not continuous but is analytic. And f of z is neither continuous nor analytic. Okay, so here we have 4 different options. All 4 of them are dealing with the function being continuous or analytic. So before we get into this, we have to understand under what circumstances a function is called continuous or analytic. So I'll put down the definition here for you. First, let's look about when a function is said to be continuous. Okay, continuous. So a function is said to be continuous at some point. Let's call the point x is equal to a, when two certain conditions should be satisfied. A function is said to be continuous at a certain point x is equal to a when two things. The first is when f of a exists. Okay, so we should be able to see if f of a exists. Then limit x tends to a, f of x exists. Now these are the two basic conditions. We also have a third condition which says that f of a should be equal to limit x tends to a, f of x. Generally, if limit x tends to a, f of x exists, then f of a would equal to limit of x tends to a, f of x. So if these conditions are fulfilled, then the function is known to be continuous. So if we take a look at the function given to us, f of z for a certain variable z, complex variable z, and its conjugate. So let me just write that down here on the side. Now let's assume that z is x plus iy. Now because the question says that x is a complex variable, let's assume that z is equal to x plus iy, where this is a complex term. Now the conjugate, or z conjugate, z star, would be written as x minus iy, since it's conjugate. This is z's conjugate. So we have z and z conjugate. Now let's take a certain point a. At x is equal to a, we see that f of a definitely exists for both of these terms. If we add them both, z plus z conjugate, since that is our function f of z, we get x plus iy plus x minus iy, which is 2x. 2x. Let me just take another sheet of paper and we'll continue here. So we have f of z is equal to 2x. So at a certain point, x is equal to a, f of a is equal to 2a. Right, so we substitute a over here and we get the term as 2a. So this means that f of a exists. So that's our first condition proved. Now the next condition says that limit x tends to a, f of x exists. Limit x tends to a, f of x, so that's f of z, which is supposed to be limit z tends to a to x. Or since this is in terms of x, we can say x tends to a to x. So it definitely does exist. This will give us 2a. Next condition says that f of a should equal to limit of x tends to a, f of x. Now what is f of a? We found that f of a is 2a. So 2a is equal to limit x tends to a, f of x is also 2a. So this is satisfied as well. Now because of all of these conditions being satisfied, we say that the function f of z is continuous. So that's our first part proven. Now we have to see if the given function is analytic. So that's our next part. Now in order to see if a function is analytic, we have to use Cauchy-Riemann's equation. Cauchy-Riemann, one of the two Cauchy-Riemann equations denotes that dou u by dou x should be equal to dou v by dou y. Okay, so let's just keep this in mind while checking if the function is analytic. If dou u by dou x is equal to dou v by dou y, then we say that the function is analytic. If it is not, then it is not. That's about it. So let's begin. We have f of z is equal to z plus z conjugate, and we found that to be 2x. So if we were to write it as a complex term, let's write this as 2x plus I0. And let's assume that this is u plus iv. Now comparing these two, we see that u is equal to 2, v is equal to 0 or 2x. u is equal to 2x, v is equal to 0. So dou u by dou x, if we take now the partial derivations of each, dou u by dou x is 2, dou u by dou y is 0, dou v by dou x is 0, and dou v by dou y is also 0. Now look at the Cauchy-Riemann equation over here. So dou u by dou x should be equal to dou v by dou y. But we see here that dou u by dou x, 2, is not equal to dou v by dou y. So I'll write that down here. So since dou u by dou x is not equal to dou v by dou y, it is not analytic. So we find that now the function f of z is continuous, but it is not analytic. So we'll take a look at the options given here. Is continuous but not analytic? The answer is B. Well, I hope this has helped. Here's the next question, number 7. A 3 by 3 matrix P is such that P cubed is equal to P. Then the eigenvalues of P are, so we have our 4 different options. So it has been given to us, we have that P is a 3 by 3 matrix, and also P cube is equal to P. Now since we are talking about eigenvalues, let's assume, let lambda be an eigenvalue of P. So if lambda is an eigenvalue of P, lambda satisfies the equation given to us. So lambda cube is equal to lambda. Now let's write this as an equation form. Lambda cube minus lambda is equal to 0. Take lambda common, we get lambda square minus 1 is equal to 0. So if we were to solve this and find its roots, I'll just put that down over here. We get lambda is equal to 0 and lambda square minus 1 is equal to 0. So lambda is equal to 0 is already a root. It is so lambda is equal to 0 is our first value. And the next one shows us that lambda is equal to plus or minus 1. So these are our values of lambda, or the eigenvalues are 0, minus 1 and 1. So this matches option D. I hope this has helped. Here's the next question, number 8. The solution of the differential equation for t is greater than 0, y double dash t plus 2y dash of t plus y of t is equal to 0, with initial conditions y of 0 is equal to 0 and y dash of 0 is equal to 1 is, we have our 4 options. The question also tells us that u of t denotes the unit step function. Okay, so we have to solve the given differential equation using the initial conditions given. So I'll just write that down over here. So our differential equation is y double dash of t plus 2y dash t plus y of t is equal to 0. Initial condition given to us, y of 0 is equal to 0 and y dash 0 is equal to 1. So these are the initial conditions. Okay, so a very good way of solving this differential equation is to use Laplace transforms. So to use Laplace transform, it is important that we know our formulas. So for this question, I'm going to write down the basic formulas over here on the side. So we'll be using first Laplace transform to convert this in the S domain and then use inverse Laplace to bring it back in terms of the exponential function. So just to give you a review of all of this, I'm going to write down only the formulas that we'll be using for this equation. So the first one is the Laplace of f dash t. Since we are dealing with differential equation, we have both first derivative and second derivative. So the Laplace of the first derivative is s f dash of s minus f of 0. The second equation is for f double dash t, and that's s square f dash s minus s f of 0 minus f dash of 0. So this is our formula for the second derivative, Laplace transform of the second derivative. Then we will also be using inverse Laplace. So the inverse Laplace of 1 by s minus a is e power at. Also Laplace inverse of 1 by s minus a whole square is t into e power at. Now I want you to keep all of these four formulas in mind. Okay, it's quite important because most commonly these are used. So I'll just take another sheet of paper here and we will begin with the solution. Okay, I think I have it straight. Alright, so let's begin with the differential equation given to us. So we have y double dash of t plus 2y dash of t plus y of t is equal to 0. I'll put down the initial condition here so that we can refer to it when we need it. Okay, so we are going to apply Laplace transform. On both sides, on the equation. Alright, so we have Laplace of y double dash of t plus 2 times Laplace of y dash of t plus Laplace of y of t. Okay, so double dash of t. Now we've saw the formula already. So here we will have s square y bar minus s y of 0 minus y dash of 0 plus, now we're writing the Laplace of this, so it's 2 into Laplace of y dash t is s y bar minus y of 0 plus Laplace of y of t is y bar. Okay, so we have this. Now you should know that y bar is actually just Laplace of y. That's the general notation. Instead of writing Laplace of y, we write it as y bar. Okay? So, next. Now that we have all of this, let's substitute the initial conditions that's given to us. Y of 0 is 0. So, y of 0 is 0 over here. So, this term becomes 0. Y dash of 0 is equal to 1. So, here this becomes 1. And this again is 0. So, let's just substitute. Y square, s square y bar minus 0 minus 1 plus 2s, multiplying that, y bar, this is 0 plus y bar is equal to 0. Okay, so this is what we have now. Next, I'm going to take y bar common and take the constant term to the other side. So I'll have s square plus 2s plus 1 y bar is equal to 1. Now y bar would be 1 divided by s square plus 2s plus 1. If we were to factorize this, we get s plus 1 square. So we have s plus 1 square. And recall that I have written the formula here for 1 by s minus a whole square. We'll be using that in the next step. So we are going to apply Laplace inverse on both sides. So I think I'll just flip this over and write it down here for you. Okay. So applying Laplace, inverse Laplace on both sides. Okay, so we have here y bar is equal to 1 divided by s plus 1 whole square. So let's apply Laplace inverse to this. Okay, so Laplace inverse of y bar is y of t. That's because y bar, like I said here, I showed you here that y bar is Laplace of y. So L inverse of L of y is y. So I'll just put that down. So L inverse of y bar is y. That's y of t is equal to. So here we have 1 by s plus 1 whole square, and we saw from the formula that 1 by s plus a whole square, the Laplace inverse of that is t into e power minus t. It is minus t because this is 1. So that's at. So substituting 1 in terms of a, in place of a, we get e power minus t. So because the question talks about unit step function, so we would multiply this with u of t. So this gives us the final answer of y is equal to t e power minus t u of t. This is the final answer, and let's take a look at which option it matches with. It matches with A. So A is the right answer here. I hope this has helped. Here's the next question, number 9. The value of the line integral of 2x y square dx plus 2x square y dy plus dz along a path joining the origin and the point 1, 1, 1 is, so we have our 4 options, 0, 2, 4, 6. Okay, so we need to find out the value of the line integral given to us. So the integral of 2xy square dx plus 2x square y dy plus dz. So we have 3 variables x, y and z. So it is important for us to change the 3 variables given into a single parameter. Let's take the parameter as t. Okay, so we have to find out the value of the line integral joining the points, the origin 0, 0, 0 and the point 1, 1, 1. So we start by finding out the equation of line joining the origin and the given point. So the equation of the line joining 0, 0, 0 and 1, 1, 1. Okay, so recall, you should be quite familiar with this already. In order to find the equation of the line, this would be x minus 0 divided by 1 minus 0, y minus 0 by 1 minus 0, z minus 0 by 1 minus 0 is equal to the parameter that we have taken as t. You can take it in terms of any letter. That's fine. So here we see this is actually the equation. So here we see that we get x is equal to y is equal to z is equal to t. And if we were to find the derivative, we get dx is equal to dy is equal to dz is equal to dt. So now that we have the terms, the three variables in terms of the parameter t and dt, next step is to substitute these into the line integral given to us. So let me just grab a sheet of paper here. Okay, so we have 2xy squared dx plus 2x square y dy plus dz. Now we change all of these terms in terms of t and dt. So this implies, so we have 2 times t square dt plus 2 t square t dt plus dt. Right, okay. This is the entire part, integral of the entire equation. Alright, next step, let's simplify this further. We get 2t cube dt. I'm going to split it, so I'm applying the integral for each term. 2t cube dt plus integral dt. Now since this is from the origin 0, 0, 0 to 1, 1, 1 in terms of just the parameter t, the integral is from 0 to 1. Now we have here 2t cube, we have here 2t cube, so we can just add them up and solve later. 0 to 1, 4t cube plus 0 to 1 dt. Now we find the integral. So the integral of 4t cube is 4t power 4 by 4 plus integral of dt is t, and all of this from 0 to 1. So we evaluate, we will get, we can ignore this value of 0 because anyway it's going to come to 0. So if we evaluate for the upper limit here, we get 4 times 1 divided by 4 plus 1. And that's 1 plus 1, which is 2. So here our final answer is 2, which matches the option B. Well, I hope this has helped. Here's the next question, number 10. Let f of x be a real periodic function satisfying f of minus x is equal to minus f of x. The general form of its Fourier series representation would be. So we have 4 different options given to us. Now in this case, we will have to check with each option in order to see which equation satisfies the given condition of f of minus x is equal to minus f of x. Okay, so if you recall, this is quite familiar. So you see f of minus x, when this is equal to minus f of x, such a condition says that the function is an odd function. And again, if you go back and recall some of the basics of trigonometric functions, we see that cos is known to be an even function, while sine is supposed to be an odd function. So this helps us. So you see, these are clues for us. So if the condition indicates that the function is odd, which means that we are looking for a sine function. So in all of these 4 options, we see that there is a sine term over here in option B, and there is a sine term here in option D. So that rules out A and C. Now let's look a little closer at options B and C. Now in option B, we see that there is just one term, sine of sine x kx. So this is just one term. But here we have sine of something plus something. So let's consider it to be sine of a plus b. Now you should remember what the formula for sine a plus b is. So sine of a plus b is sine a cos b plus sine b cos a. So here we have cos b term, we have cos a term, which means that there is a cos term, and a cos term is then an even function. So we are looking for just a sine function, which means that option B is right. Option D is ruled out. Option B is the right answer. I hope this generalization has helped. Here's the next question, number 11. A resistance and a coil are connected in series and supplied from a single phase 100 volts 50 Hz AC source as shown in the figure below. The RMS values of plausible voltages across the resistances VR and coil VC respectively in volts are. So plausible means the voltages that can flow through those certain elements. So we are looking for any one of these four options. Let's see if we can find them. Now, in order to solve this, I think the best way to do it is by drawing a phasor diagram, because here our source is an AC source, so it always helps in order to see how the phasor diagram looks like. So since it is a AC source, we have the VC that is given over here, the coil, okay, the current and the voltage across this certain coil here. So VC is our hypotenuse. The angle phi denotes the angle at which the source is running at. So our horizontal component is VC cos phi. Our vertical component would be VC sin phi. Okay, so VR, we know that the phasor of VR is always in phase, so we draw this line here, which is VR, and the resultant of VR to the point at the very end, okay, it's supposed to be a straight line, okay, so this would be the source Vs, okay, so we have the source over there. Now, based on this, we can write down an equation. So let's take the entire triangle. We write the equation, we use Pythagoras theorem. Vs square is equal to, now the sum of these two. So we have VR plus VC cos phi whole square plus this component here, VC square sin square phi. If we are to expand this, we get VR square plus VC square cos square phi plus 2 VR VC cos phi plus VC square sin square phi. Now this term here, VC square cos square phi and VC square sin square phi term becomes 1, since we know the relation that sin square theta plus cos square theta is equal to 1. So let's simplify. We'll get another sheet of paper here. Okay, so utilizing that, we get Vs square is equal to VR square plus VC square into sin square phi plus cos square phi plus 2 VR VC cos phi. So this is our expression. We used the relation earlier to turn this into 1. So we get VR square plus VC square plus 2 VR VC cos phi. So from here we can take out the expression for cos phi. So cos phi can be written as Vs square minus Vr square minus Vc square divided by 2 Vr Vc. So if we check the values that have been given to us, 65, 35, 50, 50, 60, 90, 60, 80. So basically we are supposed to find out what values of Vr and Vc would we get the cos phi as 0. So we have to check for each of these values here. So that's our aim. We are supposed to see that which values of Vr and Vc. The first set of values here correspond to Vr and the second set correspond to Vc. So if you substitute 65 in terms of Vr, 35 in terms of Vc and 100 in terms of Vs, you should be able to get the value as 0. So check. So you will notice that A doesn't work. So you will have to substitute for each one. A, B, C and D. So according to the calculations, we see that D satisfies 60 and 80. So we'll just check that. So that's 100 square minus Vr is 60 square minus 80 square divided by 2 times 60 into 80. So if you solve this, you will notice that this is 0. So for all values for which cos phi is 0 is the right answer. So here D is the right answer. I hope this has helped. Here's the next question, number 12. The voltage V and current A across a load are as follows. V of t is given as 100 sin omega t. I of t is given as 10 sin omega t minus 60 plus 2 sin 3 omega t plus 5 sin 5 omega t. The average power consumed by the load in watts is dash. So this is not a multiple choice question, so we will have to work it out. Now we have been given the equation for voltage and the equation for current. So we have to find out the average power. Average power, now based on the equations, you will notice that it is in terms of AC. So the average power is given Vrms times Irms into power factor cos phi. Now Vrms, Irms in terms of peak voltage and peak current is Vm by root 2 into Im by root 2 into cos phi. Now here you will notice that in current equation we have 60 over here in place of the angle, angular frequency. So here that indicates that phi is 60 degrees. So that's omega t minus phi. So this indicates that our phi is 60. So we substitute that over here. Now we need the values of Vm and Im. Now Vm is the peak voltage value. So look at the equation for voltage given to us over here. 100 sin omega t. 100 is our peak value. For current, it is 10 sin omega t minus 60. Sure, there are other values, other terms in the current, but since the first term consists of the angle, this is going to be our peak current. So substitute the values. We have 100 divided by root 2 into 10 divided by root 2 cos 60. So if we solve that, we get the answer as 250 watts. So 250 watts is the final answer. So you will have to keep a few points in mind. When you have an equation with too many terms in the current equation given in the question, so you will have to note the term in which phi exists in. So here in the entire term, since the first term consists of the angle of omega t minus phi, phi is taken from that term alone. So you don't have to utilize the other two terms. Okay, so sometimes there are just a few tricks that we use. Well, I hope this has helped. Here's the next question, number 13. A power system with two generators is shown in the figure below. The system that consists of generators, buses and transmission lines is protected by 6 overcurrent relays R1 to R6. So we have here R1, R2, R3, R4, R5, R6. Assuming a mix of directional and non-directional relays at appropriate locations, the remote backup relays for R4 are. Okay, so we have to take R4 into consideration in the entire equation. The remote backup relays for R4 are. Okay, so if a fault takes place between 3 and 4 here, now let's say that a fault occurs here. So if a fault occurs between 3 and 4, then relays 3 and 4 must operate. Okay, but when, let's say for example, a relay fails, if any one of these two relay fails, then there are two currents that need to be in check. We have to keep in mind of the current I1 and I2. These two currents must be limited. I1 from the first generator and I2 from the second generator here. These are the two currents that we need to limit. So in order to limit I1, R1 must operate. And in order to limit the current I2, R6 must operate. It's the very first relay that needs to operate. So if any fault occurs and if a certain relay fails, according to this question, if R4 fails, then R1 and R6 must operate. So in this question, the remote backup relays for R4 are R1, which corresponds to the current I1, limiting current I1, and R6, limiting current I2. So that's R1 and R6, option D. I hope this has helped. Here's the next question. A power system has 100 buses including 10 generator buses. For the load flow analysis using Newton-Raphson method in polar coordinates, the size of the Jacobian is. Okay, so we have been given 4 options, the sizes of Jacobian matrix. So we will have to find out which one is right. So first let's note down what has been given to us. So the power system has 100 buses. So the total number of buses given, total number of buses 100. The question says that 10 generator buses are included. So generator buses 10, which means that the remaining buses are load buses. Load buses would be 100 minus 10, which is 90. Now, since we are finding out the Jacobian, we will write the generator buses, we'll denote them as N, and we'll denote the load bus as M. Okay, so we have notations given to generator and load bus. So in order to find the Jacobian size, we can use the following formula. The size of the Jacobian matrix is, okay, so the formula is 2m plus n minus 1 by 2m plus n minus 1. So this is the general formula for the size of the Jacobian matrix. We have m as 90, n as 10. So let's substitute. We will get 2 into 90 plus 10 minus 1 by the same, 2 into 90 plus 10 minus 1. So that's 180 plus 9. So it is 189 by 189. So the size of the Jacobian matrix is 189 by 189, and that matches option A. So this is the final answer for this question. Here's the next question, number 15. The inductance and capacitance of a 400 kV 3-phase 50 Hz lossless transmission line are 1.6 millihenry per kilometer per phase and 10 nanofarads per kilometer per phase respectively. The sending end voltage is maintained at 400 kV. To maintain a voltage of 400 kV at the receiving end, when the line is delivering 300 megawatts of load, the shunt compensation required is A. capacitive, B. inductive, C. resistive, or D. 0. Okay, so first you will have to understand what shunt compensation is. So shunt compensation is a method that's used to improve the power factor. So that's the basic definition. It's just a method used to improve the power factor. The closer the power factor is to unity, that's the best that it can get. So the shunt compensation is a method used to improve power factor. So when we use an inductive load, or when an inductive load is connected to the transmission line, the power factor lags because of lagging load current. And in order to compensate that, a shunt capacitor is connected, which then draws a current leading the source voltage, and thus that improves the power factor. So let me just write that down here as well. That's just an example of what shunt compensation is. So if we were to have an inductive load that is connected to a transmission line, okay, so in this case the power factor lags. For an inductive load, the power factor would lag, and that is because of the lagging load current. And in order to compensate this lagging power factor, we connect a capacitor. So this draws a leading current. So here the power factor lags, it's because of lagging current. And if we connect a capacitor, it draws a leading current. So this compensates the entire system and hence improves the power factor. So this improves the power factor. So this is an example of how the system works. So if there was an inductive load, then by connecting a capacitor, we would improve the power factor. So here the shunt compensation is capacitive. So this is an example. Okay, it's an example. Alright, so now we have to figure out for the question given to us. Now let's look at the surge impedance of the system given. Now we have been given the inductance as well as the capacitance value, so we can find out what the surge impedance is. Let me just get another sheet of paper here. Right. Okay. So let's calculate the surge impedance. ZS. The surge impedance is given in terms of root L by C. We have already been given the values of L and C, so let's substitute that. L is 1.6 10 power minus 3 divided by capacitance is 10 into 10 power minus 9, square root of that, and the square root of this comes around to 400 ohms. Okay, so we have the surge impedance. Now let's look at the load impedance. The load impedance ZL. So ZL can be calculated in terms of the power that's given. We have been given, let's see here, 400 kV and a load of 300 megawatts. So the load impedance is kV square divided by the load power. So 400 10 power 3 square divided by 300 into 10 power 6. So all these formula here you will have to remember. It's good to keep in mind the surge impedance formula and the load impedance formula as well. Okay, so calculating the load impedance, we get a value of ZL is equal to 533.33 ohms. Now this tells us that the load impedance is greater than the surge impedance, right? So ZL is greater than ZS. Now when ZL is greater than ZS, that indicates that the receiving end voltage will be more than the sending end voltage. So VR is greater than Vs. So in order to reduce this voltage and to keep it to a level of 400 kilovolts, that's what has been asked, see? To maintain a voltage of 400 kilowatts at the receiving end. Now because the load impedance is greater than the surge impedance, we come to the relation that the receiving end voltage is greater than the sending end voltage. So in order to keep the receiving end voltage at 400 kilovolts as what the question says, we would need an inductive compensation. So, but if Vs were greater than Vr, it would be the opposite. We would need capacitive compensation. So, I hope this generalization helped. So, the final answer here is inductive. That's the final answer. Here's the next question, number 16. A parallel plate capacitor filled with two dielectrics is shown in the figure below. If the electric field in the region A is 4 kilovolts per centimeter, the electric field in the region B in kilovolt per centimeter is A, B, C, D. So we have 4 options. Now, there are questions like these where you have to go to the very basic of what we have learned. And for a parallel plate capacitor, you have to remember that the voltage is the same for both regions. So that's an important point. For a parallel plate capacitor, the voltage is same for both regions. And if the voltage is same for both regions, that means that the electric field is same as well. So we know that the electric field V by D ratio is constant for different regions of the parallel plate capacitor. So if the electric field in region A is 4 kilovolts per centimeter, the electric field for region B would be 4 as well. There is no change. So the final answer here is 4. I hope this has helped. Here's the next question, number 17. A 50 MVA 10 kV 50 Hz star-connected unloaded 3-phase alternator has a synchronous reactance of 1 pu and a subtransient reactance of 0.2 pu. If a 3-phase short circuit current close to the generator terminals, the ratio of initial and final values of the sinusoidal component of the short circuit current is dash. Okay, so we see here that there's a lot of information given to us. So just because there's so much, let's write all of it down. So we have been given that The system is a 50 MVA, 10 kV, 50 Hz, star-connected, unloaded, 3-phase alternator. We have also been given that the synchronous reactance, XS, is 1 per unit. Subtransient reactance, let's call that, I'll just write that down as XT. XT is 0.2 per unit. So during the transient period, the short circuit current is 1. Okay, so we will have to keep that in mind. Short circuit current would be 1 pu. So the short circuit current is, in this case, in a 3-phase alternator, short circuit current is inversely proportional to the reactance X. So this is an important relation. This is the relation that is going to actually help us to solve the problem. So if this is the relation, from here we can write a ratio of the currents in both instances. So if we were to write IS by IT, that would be equal to XT by XS. Since it is inversely proportional, we would have this relation here. Now we have that XT is 0.2 and XS as 1. Now we need the ratio of initial to the final values of the sinusoidal component. Initial to the final, which means, now if we were to just write this in those terms, initial and final value, we have been asked to write down what is IT by IS, initial to final values. So that in terms of the reactances given to us would be XS by XT. So we have the value of XS to be 1. We have the value of XT as 0.2. 1 by 0.2 is 5. So this is the final answer here. The ratio of the initial and final values of the sinusoidal component of the short circuit current is 5. I hope this has helped. Here's the next question, number 18. Consider a linear time invariant system with transfer function h of s is equal to 1 by s plus 1. If the input is cos t and the steady state output is a cos t plus alpha, then the value of a is dash. Alright, so we have been given the transfer function of a certain system. So the transfer function is given to us as h of s is equal to 1 by s plus 1. The input is given to us as cos t and the output is given as a cos t plus alpha. Now here a is the amplitude. So we need to find out the value of this amplitude. Alright. Now in terms of the transfer function given to us, the amplitude a would be mod of h of s, or the magnitude of the transfer function given to us, which is 1 by s plus 1. And the amplitude of this in terms of j omega, h of j omega, would be 1 divided by root of omega square plus 1. So we are converting this in terms of omega. So 1 by s plus 1 is written as 1 by root of omega square plus 1. Now this is because the input is given as cos t. So if the input is cos t, that means this is x of t. So if x of t is cos t, omega is 1 radian per second. Okay, so if that is what we will have to do here, we have to substitute the value of omega here in order to get the value of a. So now from here we see that omega is equal to 1 radian per second. So if we substitute this over here, we get a is equal to 1 by omega square plus 1, which is equal to 1 by root of 1 plus 1, which is 1 by root 2. So 1 by root 2 in decimal form is 0.707. So that is the final answer here, 0.707. I hope this has helped. Here's the next question, number 19. A three-phase diode bridge rectifier is feeding a constant DC current of 100 amps to a highly inductive load. If three-phase 415 volt 50 Hz AC source is applying to this bridge rectifier, then the RMS value of the current in each diode in ampere is. Okay, so considering what's been given to us, we have IDC, the DC current, as 100 amps. Now if we had to find out the RMS value, I RMS is equal to Im by root 2, where this is the peak value. So we don't know what the peak value is. So we have to find out what Im is. And Im can be found by this relation here in terms of bridge rectifier. So these formulas are for bridge rectifiers. So it's I naught root 2 by 3. This is the formula that you would need to remember for a diode bridge rectifier. So if we substitute this over here, our formula now becomes I RMS is equal to I naught root of 2 by 3 divided by root 2. So in other words, it's just I naught by root 3. And I naught is IDC of what we have found here, okay, which is 100. So 100 divided by root 3, which gives us 57.735 amperes. So this is the final answer here, 57.735. I hope this has helped. So to make it easier, all you have to do is look for the specific terms in the question. Now, since the question is talking about a diode bridge rectifier, certain equations or certain formula should pop into your head. So it always helps while you're studying theory, the theory part of it, note down all the important formulas under the certain topics, under your topics. Note them all down, write them a couple of times. I assure you that they will help while you're solving problems. Here's the next question. Number 20. A buck boost DC to DC converter, shown in the figure below, is used to convert a 24 volt battery voltage to 36 volt DC voltage to feed a load of 72 watts. It is operated at 20 kHz with an inductor of 2 millihenry and output capacitor of 1000 microfarad. All devices are considered to be ideal. The peak voltage across the solid state switch in volts is dash. Sometimes the circuit given to us and the information given in the question is quite large and there's a lot, but you will have to try your best to break it down in a way that it actually becomes quite simple. Now here, they are talking about a buck boost DC to DC converter with a lot of information. It is shown that it converts a 24 volt battery voltage to 36 volt DC voltage. A load of 72 watts is given to us, and the operating frequency is given, the values of inductor and capacitor is given, a whole lot is given to us. But the question talks about the peak voltage across the solid state switch S. Now the peak voltage across this is when the switch S is turned off, because when the switch S is turned off, the diode D turns on. See, those are the basic points that will help you solve your problem. So you will have to know how a buck boost converter works. So here's the important point. When the switch S is turned off, diode D is on. So in this case, what happens to the circuit is that where the switch is, it becomes open, and we have our voltage source here, we have our inductor here, and we have the load given to us. So since the question talks about voltage, keep your mind on the voltage, keep your eyes on the voltage as well. Here across the load we have 36 volts, which means the 36 volts is the same amount that is passing through this point here. And we have 24 volts for the source. So the peak voltage across the switch, across the solid state switch S, this is our S. Now across that point would be just the sum of both the voltages. So we have our peak voltage as the sum of 24 volts plus 36 volts. 24 volts plus 36 volts, that will give us a value of 60. So this is our final answer, 60. I hope it has helped.